Okay, so if we start with the first problem on the first page you sent me, we have the information that when x is greater than 0, we have this y equals 2 asymptote. So if I just kind of sketch this to kind of go through some of the options of what we have, we only really have information about the right side of the graph or the positive versions. What we do know is that there's this asymptote that runs at y equals 2, and really we only know that it's applicable for everything greater than 0. So we could actually go back and erase the left side because we don't really have any information about when x is negative. So we have to identify which one of the statements has to be true. So if I just go through them, one statement says f of 0 equals 2. Well, that would mean when x is 0, our y is equal to 2. Well, we know that we have this asymptote here, so more than likely we're not going to be able to put in 0 for x and get 2 because that would put us right on that asymptote because we know y, if this is an asymptote, y should not be able to equal 2. So this would have to be false. Then we have f of 2 is undefined. So this was kind of our first option. We also have the option that f of 2 is undefined. That's actually also going to be false. Now keep in mind what this notation is. We're saying that when x is equal to 2, we don't have a y value. Well, that's not true because here's 2 for x. We don't know where that graph is. That graph could be up here, could be down here. So we can have values for x when x is 2. We can't have values for y when y is 2. So just be careful with this. This is when x is 2, we could have a value because let's say, for example, the graph does something like this. Well, when x is 2, we do have a point. We just can go up to when x is 2. We do have a y value that we can find. So we don't really know. And even if the graph was climbing up towards the asymptote when x is 2, it would be somewhere on the curve. So the value of 2 for x is still defined. We don't have an issue with that. So this would be false. Okay. The third option they give us, they say f of x can't equal 2 when x is greater than or equal to 0. Now you might think, okay, well that should be true because they tell us we have this horizontal asymptote, so there's no way that we should be able to get a y out for our value. The only issue with this is actually going to be false, is because what can happen and what often happens sometimes with horizontal asymptotes, we can cross them. So the graph might actually do something like this. So it may be able to cross, or it may be able to come down this way and cross over the asymptote. So regardless, because there's a possibility that the graph could cross the asymptote, at this exact value, the graph actually does equal 2 for y. So this isn't necessarily, it's probably 99% of the time true, but not always true, because we can cross that asymptote, and when we cross it, the y value just for that point would be at 2. And then the last statement we have is, or two more statements, let me dump them over here, is they say that the limit as x goes to 2 is f of x, or y goes to infinity. Now the only issue with that statement is, again, it's based off of when x is 2. We don't know what happens when x is 2. All we know is what happens when y equals 2. That's where our asymptote is. So because we don't know anything about what's happening when x is 2, we can't really say for sure whether that's true or false. So we'd have to say it's false since we don't know that it's 100% true. Because, for example, it really all depends on where the graph is and what the graph looks like. So if the graph is doing something like this, then when x approaches 2 from either direction, so as we approach 2 from this way, we're approaching this y value. And as we approach 2 this way, we're approaching that y value, but we don't know what that number is. And regardless of the way that I drew it, if this is an asymptote, more than likely, as we approach 2, we're not going to be able to be going to infinity. So a graph like that would support this would be something like, we would have a vertical asymptote at 2, and it would be some type of graph that's maybe doing something like this. So as we approach 2, we're going to infinity. Well, that's not the case. We don't know, they didn't tell us anything about having a vertical asymptote. They just said a horizontal asymptote. So we can't say for sure where the graph is going as far as the x is concerned. Now what we can say is, since this is an asymptote, and even though we may cross it, usually we only are able to cross asymptotes once. And when you cross the asymptote, you usually still come back to the asymptote. So as an example, we may cross the asymptote, let's say like this, but then we usually come back towards the asymptote. So one thing we can say for sure is that as x gets bigger, because remember our original information was about things greater than x, as x gets bigger, the graph itself is probably going closer to 2. Because as x gets bigger, the graph is getting closer and closer and closer to that asymptote. So this one, which I think is your last answer option, would have to be true just because of how limits work. For limits, as x gets bigger, we always approach that horizontal asymptote, and that's something that's always true for calculus. Okay, so then if we go to the second one that's on that page, this one's going to require a little bit of simplifying. So before we actually jump into it, I'll give you a kind of example and we can apply that same concept. So if we have, let's say, the limit as x approaches 3, and we have the equation x squared plus 2x over 4. The way that you guys have talked about it in class is that when you have a numerical value here, assuming that this is not going to make this be undefined, you can actually take that number, which is 3, and we can plug it in for the x values. So you would do 3 squared plus 2 times 3 over 4, and then you would solve and get your number. We're going to do that same type of strategy with the question that they gave you. The only difference is they didn't give you a number for your limit. They said the limit as x goes to a, which is a variable. So that's fine. We're just going to tackle it the same way. Just like we could put 3 in for the variables, we're going to put an a in for the variables. So let me write. So all we're doing is substituting it in, just like we normally would if we had a number. Okay, and the equation you have x squared minus a squared over x to the 4th minus a to the 4th. Okay, so we are going to do what we would normally do if this happened to have been a number. We're going to put a in for the x values because that's our variable. The a is some number, some constant number. So we're not going to obviously substitute a in for a because it's already there. But what we'll do is instead of x, we're going to put an a. So this would be a squared minus a squared over a to the 4th minus a to the 4th. Now one thing that you'll notice is you might say, well, a squared minus a squared, obviously that's 0. And a to the 4th minus a to the 4th is also 0. Well, 0 divided by 0 is actually undefined. So we have a problem with that. So we can't actually simplify it like that. We actually are going to have to try to get rid of some factors. So there's more than likely when you always get 0 divided by 0 when you try to find your limit, that means you have to go back and simplify. There's something in this equation that should be able to cross out or simplify. So that just is a little marker for us that we need to go back and simplify this more. So I'm not going to just subtract and say it's 0 over 0. So I'm going to factor. So keep in mind, both of these are squared. So this would actually factor into a plus a. It's going to look really awkward. And a minus a. Okay? Just like if we had x squared minus 1, we would make it x plus 1 and x minus 1. It's kind of the same type of idea that what we're doing. But it'd be a plus a and a minus a, which again does look really awkward, but we'll keep it that way for a second. Divided by, now a to the 4th. Okay? If we think about x to the 4th minus 1, that's the same as saying x squared minus 1 times x squared plus 1. Okay? We can tackle this the same way. We're going to do a squared minus a squared and a squared plus a squared. Okay? Now nothing looks like it can cancel, but these are two squares. They're the difference of squares we're subtracting them. We can factor that even further. So let me jump up here. I'm just going to erase this and I'll rewrite what we have so far. So far on the top we have a plus a times a minus a all over. Now we have a squared minus a. We can factor that to be a plus a times a minus a. And then we still have this here. a squared plus a squared. Okay? So just to kind of recap, because I know this is really confusing with all these a's. This a squared minus a squared, think of it as like x squared minus 4. They're both squared, so we can do the square root of each of these. So this is really x plus 2, x minus 2. This is the same type of strategy I've used for that. Since they're both squared, it's a plus a, or square root of this plus the square root of that, times a minus a. Okay? Now the good thing about that is if we go up here, we see some things can cancel. Here's an a plus a, that can cancel with that a plus a. Here's an a minus a, that can cancel with that. So really what we're left with is nothing on the top, so a 1 over. The bottom is a squared plus a squared. And now we can actually add those together like we normally would for variables. So if it's a squared plus a squared, that's just 2 of them. So 1 over 2 a squareds. And that would be as far as we can go because we don't know what a is. So to kind of recap, even though it started off with the limit as x approaches a, we just take a and put that in for all the x values, and then we simplify it. Okay, so then if we go to the next page you sent me, which deals with trying to make functions continuous, the really super easy way, I'll show you kind of what it means, what they're asking for you to do, and I'll show you a really easy way to do it. So for the first one, you have x squared plus 1 when x is less than 3, and x squared plus 6x plus c when x is greater than or equal to 3. So the issue with this is a piecewise function. It probably has a gap somewhere in the graph. Now, if I look at the top equation, since the top equation we have all the information we need, if I were to graph that, this is a parabola that's up 1, so it probably looks something like this. The only issue is we only want this equation for everything less than 3. So let's call this 3 right here. So the graph, if I go back and modify it, we have a big open circle at 3, and then the rest of the curve. So what we want to make sure is where this equation stops is where this equation starts, so that it's continuous, so that we don't have a gap. So ideally, we want to make sure that this point right here is also a point included in this graph, so that they can overlap. Now what we'd have to do, I'll show you one way and then I'll show you an easier way. We'd have to figure out what this y value is. We don't know what that y value is. We need to know that so that we can make sure that this graph has that y value. So what we can do is take 3 and plug it into that top equation. So if we take 3 and put it into the top equation, we get 10. So this point is 3, 10. So this y value is 10. So that tells us that we would want to make sure that the point 310 is included in this equation so that they can overlap. So what we can do for that is we can take this equation and we know we need to make it equal 10. We need the y value to be 10 and we need the x value to be 3. So you can actually go back and replace the x's with 3. Okay, so we get 9 plus 18 plus c equals 10. So 27 plus c equals 10. We subtract, c would have to be 17. So that means that in order for this equation to stop and have this equation pick up exactly where that one left off, this has to be 17. So that when we plug in 3, we get 10, which is this equation here. When we plug in 3 to this, we'd get 10, which would put us right here. And actually, sorry, this is a negative 17. So this is minus. So that way that other equation would probably do something, let's say like that. So where this one stopped, that one picks up, so really there's no gaps in the graph. So that's like the longer explanation of what we're doing. The easiest way to do it is just set the two equations equal to each other. And that will work every single time, even if it's a really complicated problem. So I'll show you that same equation, but with the easier approach. So the first thing we want to do, if we talk about it in steps, is we just set two equations equal to each other. And then the second thing we do is we put in x value and solve. Now, when we say the x value, they will tell you, like if you notice on the right side of each of those problems, it tells you like they want you to make it continuous at x equals 3 or x equals 2. They'll tell you the x value, and that's just what you put in for this x value in the equation. So the equations we had, we would set them equal to each other. So x plus 1 equals x squared plus 6x plus c. And now we're just solving for c. We already know what x has to be. We want to make it continuous when x is 3 because that's what it told us. So for all the x's, I just go back and I just put 3's. And that way, the only variable I have is c. So I get 9 plus 1 equals 9 plus 18 plus c. So 10 equals 27 plus c. And then I would have subtracted 27 both sides. So negative 17 equals c. Okay. So again, we just set the two equations equal to each other. Because what we're trying to find out is when the equations will overlap so they can make sure that they patch up any holes that might be there on the piecewise function. So for the second one, we do the same exact approach. So we would do 7x minus 2 is the first equation. We'll set that equal to cx squared. And we know that we want to make it continuous when x equals 1. So we'll go back, and for all the x's, I'll just put a 1. So I get 7 minus 2 equals 1 squared is 1, so equals c. So 5 equals c. So in order for this equation in order for this equation to have the same y value to patch up the hole that this equation leaves behind, the c has to be a 5. Right? And then for the last one, we tackle it the exact same way. We just got to set the two equations equal to each other. So we have cx squared equals 2x plus c. Okay? Now here we almost have like two c's in two different places. That's fine. We want for that equation, they tell us that we wanted to make it continuous when x equals 2. So for all of the x's, we go back and put 2's. So we get 2 squared is 4. So 4c equals 4 plus c. Now we want to get the c's on one side, so we just subtract c. So we get 3c equals 4. And then if we divide, we get c has to be 4/3. So it's pretty simple. So for these, when you're trying to make it continuous, just set the two equations equal to each other. They'll tell you the point where they want you to make it continuous. And if they don't tell you, it's always whatever the boundaries are in the piecewise function. So for the first one, it was x is less than 3 and x is greater than 3. 3 would be the number that you put in for your x. So they don't tell you specifically, but usually they'll tell you where they want you to make it continuous. So just set the two equations equal to each other, plug that number in for x, and all you'll be left with is the c value to solve for.